Hi, this is Taimur, and you are watching IEEE VTS Young Professional Seminar. This is one of the seminar from a series of seminar. It is our second occasion, and today I'm delighted to have our guest speaker, Marco Giordani. He's with us. He's a postdoc researcher and adjunct professor at the University of Padua, Italy. And topic for today's talk is towards 6G networks, use cases and technologies. So I would like to invite Marco to the stream, and then I will give the stage to Marco. Welcome, Marco.
Thank you. Thank you. Hi, everyone. And thank you, Timer, for your nice introduction and good afternoon, good morning, or good evening, depending on where you are to everybody. And thanks for attending this presentation. So let me start sharing my screen. All right. Okay. So in this presentation, I will discuss about 6G networks, and I'll try to overview the use cases that are being considered for 6G and the technologies that will make it possible for these use cases to be enabled. Before I start, let me give a brief introduction of where I come from. So I come from the University of Padua. Padua is a city located in the northern part of Italy. It's very close to Venice. And the research group I belong to is the Signet Research Group that includes several faculty members and postdocs and PhD students. And we deal with different aspects of the research in the field of networks. Most importantly, what we do research on is Internet of Things, the use of millimeter waves for 5G networks, and we also have a branch focusing on underwater networks and all these other fields that you can see in this slide here. Specifically, I belong to the 5G, 6G research group, and that's why today I'm delivering this talk on 6G. Okay, so let's start. So I want to introduce this picture here that you probably have already seen somewhere, and is drafting how the network generations have evolved over the decades. And as you can see, from 1G to 5G, every generation of mobile network has tried to meet the needs of the network operators and final consumers. But now we are already in the 2020 society, and so we are headed towards what's coming next. That is the 2030 era. And there we will need, there will be new challenges to support the ever-evolving changes of the society. And that's why the research community is leaning towards a new generation of wireless networks, which will be the sixth generation. And that's why that's where the term 6G comes from. So when talking about 6G, the first question you might have is, why should we discuss about 6G now, since 5G has just started to be commercialized? So is it really the right time to talk about 6G? Well, indeed, as you may know, a few months ago, the first ever 5G iPhone was released. And in Italy, and I'm sure almost everywhere in the world now, telecom operators are advertising 5G plans for their smartphones. So why do we talk about 6G now? Well, first of all, historically, I have to say, every new mobile generation has appeared approximately every 10 years. And the first release of 5G, 5G NR from the standard appeared and was announced in 2018. So according to this trend, we expect the 6G standard to emerge around 2030. And that's why we need, from a research community point of view, to put research efforts right now to draft the communication needs of the future, the performance requirements of the new use cases that will be enabled, and also which technological options can be developed in the context of 6G. So we can say that the time is right to start at least discussing about this new generation. And in the same way that 5G was, and 5G requirements and technologies were derived from LTE shortcomings, we can say that 6G innovations will naturally build upon what happens so far in 5G. So we are going towards the 2030 society, and we need to redefine the 5G communication and application requirements in view of the new economic and technological and the environmental context of the 2030 era. And most importantly, we need to satisfy new requirements of emerging markets and trends that 5G has not yet addressed completely. For example, let me give you a couple of examples here. Like there is still open the issue of bridging the digital divide, so providing connectivity to the rural areas. And I'm talking about broadband connectivity, so not just access to emergency services, but to the real broadband internet connection that we have in the urban centers. And then network has to be fully autonomous, and this requires some efforts from an architectural design point of view. And we also need to evaluate the energy impact of the ICT sector for the environment, which has been a target of 5G, but so far seems to be quite disregarded. And the same goes for the role of the uplink. Most of the times, telecommunication technologies are developed having downlink in mind. But now the role of the uplink is gaining more and more attention in the future society. And this means that research activities of the future will need to satisfy also a broadband uplink connectivity. And this trend is also demonstrated in the standardization activities that are being carried out within the 6G timeframe. For example, you can see here from this slide that the 3GPP is defining new study items for the next 5 to 10 years. So we are completely within the 6G ecosystem. And the ITU is also drafting the requirements of future 6G use cases. So as I was saying at the beginning of this presentation, the time is right to figuring out how the 6G networks of the future will look like. So this is going to be the outline of my presentation. I will first of all dedicate a few minutes talking about which services the future society will need to address and which requirements we will have. And then I'll present the technologies that will make it possible for these demanding requirements to be satisfied. And I want to keep the discussion as high layer as possible. So my intention is not to give you equations or numbers, but concepts. Or providing guidelines on the most promising research topics of the 6G ecosystem and stimulate further work on the 6G within the 6G perspective. We'll discuss about which new radio communication technologies can be developed at the physical layer, and also which innovations have to be brought to the MEC layer and to the architecture to make it possible for 6G to operate properly. So, but first thing first, let's start with use cases for 6G. Here is a list of possible use cases that can be enabled in 6G, and I will review some of them and provide also some guidelines towards the requirements that have to be satisfied. And I want to start with industry and manufacturing. So 6G will likely foster the industrial revolution towards the fourth or even the fifth generation. And we are talking about the digital transformation of manufacturing through the so-called cyber physical system paradigm. So the idea is to make it possible for multiple robots to cooperate together and make it possible for for accomplishing cooperative maneuvers that require a very high degree of precision and coordination. And in order to do so, we need at least two types of communications. One is intra-machine communication, like to control robotic arms. And this means replacing cables with wireless communication. And this can be enabled by innovations like new integrated circuits, which may operate in the terahertz scale. Also, we need multiple robots or multiple machines to communicate together. And this is inter-machine communication, which is particularly complicated due to the very large distances involved, as well as the mobility of the machines. So this is one aspect of the research. This industry and manufacturing is typically regarded as IIoT, so industrial IoT, which is something which goes a little beyond what 5G is considering. Another application is teleporting, is the holographic delivering of experiences in real time without head-mounted display technologies like VR or AR, as we are today, as it is typical in 5G. Teleporting will stimulate telework by allowing a flexible interaction during business events. And in this way, we can reduce and save travel time and expenses because we can be wherever we want in the world by simply digitally transferring ourselves. And especially in these particular challenging times, replacing travels with a safer way of meeting is particularly important. And there are several challenges compared to 5G. So 5G was designed to support a 2D-like communication of video and audio, while now the idea is to send also non-physical human sensing, like smell and taste and touch and so on. So how will this become possible is still to be figured out. And in 5G, the data content was broadcast regardless of the viewer's position, while now holographic telepresence implies that the parallax dimension also have to be transferred. So the image will change depending on where the viewer is located and how the viewer interacts with the image itself. The data rate requirements for this type of application is challenging, is in the order of terabits per second, and the latency will also need to go below the 1 millisecond threshold, which was imposed by 5G. We want the holographic telepresence and experience to be as smooth and immersive as possible. And this is particularly demanding for the communication protocols point of view. Another topic is related to smart transportation. So autonomous cars, let's say. And this is a use case of 5G, but I'm sure you can agree that it's pretty unlikely that we can see fully autonomous cars within a time frame of 10 years from now. So 6G will necessarily have to go along this path and enable safety and comfort in our roads, as well as providing navigation and entertainment services for drivers and passengers, including the use of AR and VR or even teleporting within the car. And one way to do so is for cars to share continuously the information acquired through local sensors. And when we have hundreds of sensors per car, the data rate is in the order of terabits per second. And the reliability also is expected to be particularly important to consider. Think about the catastrophic consequences of a communication failure within the autonomous driving use case. And so this is something that has to be carefully looked through when it's up to 6G. And healthcare will also have a very prominent role in the context of 6G. We are talking about the evolution of healthcare to support telemedicine. The idea is to transition from a traditional provider-patient relationship towards the so-called care outside the hospital paradigm. So now the primary care services will be delivered directly to the patient's home. We want to have an individualized and personalized assistant for the patients. And this is particularly important to avoid fragile patients like elderly people to move. And it's better for doctors to be digitally transferred directly to the patient homes. And this will also make it possible for robotic telesurgery to be enabled. And the reason why these challenging health use cases are not likely to be enabled in 5G is that right now we have a very major limitation poses by the absence of real-time tactile feedback in the loop. And this is something that advances in the mobile edge computing and artificial intelligence will make it possible within the 6G time frame. And finally, I want to conclude this part on use cases into discussing something that is beyond what we typically observe in the research community, and this is related to the financial world. So how we can evolve the financial sector towards high frequency trading and blockchain. So when I talk about high frequency trading, I intend a new method of trading in which we have a lot of supercomputers that can transact millions and millions of financial decisions in a fraction of a second. And you can imagine that in this scenario, even a sub-millisecond latency improvement will have a major impact in the financial domain. So it's important that communication technologies provide a sub-millisecond latency to be satisfied. And the blockchain technologies has also gained momentum in the banking industry. It's a solution to guarantee transparency and anonymity. And for blockchain to be enabled, we have a huge amount of data to be processed. And that's where 6G is headed to. We also need to provide an elevated security standard, for example, like through quantum computation or other types of innovations that 6G will develop in the next decade. So to sum up all of this, here is a list of possible KPIs for the specific use cases I've described so far that will need to be satisfied in the future society. So I have to say, these KPIs have not yet been officially clarified by the standard community. It will be in the next few years, but still we can already draw some guidelines on what these KPIs will look like. For example, you can see that we are expecting at least a 10 times improvement in terms of latency, which will go below the 1 millisecond requirement of 5G. And also data rates will need to evolve from up to 10 times improvement with respect to 5G. And as you can see, there are some other types of requirements to be satisfied, like the density of devices per square kilometer, which will reach the 10 million devices, which is at least 10 more what 5G is currently set to satisfy. And reliability will also need to go into an almost 100% reliability requirement, which is pretty challenging. So you can see here that we need new technological solutions to address these challenging requirements. And this is what I will talk about in the next in the next part, in the next half of this presentation. So let's start about the new spectrum solutions. As you may know, the 5G NR standard already introduced several innovations, like a new flexible frame structure or a new massive MIMO technology to realize beamforming. And And also the spectrum technologies will need to evolve with respect to what 5G was already supporting. Uh, in 5G, we have seen the evolution of towards millimeter wave technology, which loosely considers the frequency bands from 10 to 100 gigahertz. And we know the advantages of using the high frequency spectrum to communicate. First and foremost, the very high data rates that can be achieved. So the question is, in 6G, can we go higher in frequency, higher than millimeter waves? And the answer is yes, and we can do that by leveraging the terahertz bands and the use of visible light to communicate. So let's review the two technologies separately. So let's start with the terahertz. The terahertz frequency band operates between 100 gigahertz and around 10 terahertz. And compared to millimeter waves, we can practically bring to the extreme the potential of high frequency connectivity. And we can enable data rates in the order of hundreds or even thousands of gigabits per second, which is pretty much in line with the boldest 6G requirements I've described before. Of course, there are several challenges to be faced, and that's why research towards 6G is important. One is the propagation loss. We know that as we go higher in frequency, we also need to cope with a very severe absorption as the distance increases. Another issue is the molecular absorption. We need to choose the band, the terahertz band, to operate at very carefully in order to avoid absorption from molecules in the air. And the penetration is going to be pretty severe, as we already know from earlier studies at millimeter waves. And the way the radio frequency circuitry has to be designed if we want to operate at terahertz also deserves attention in the future. But I would say that the main issue to developing terahertz solutions is due to the propagation distance that can be achieved. We are talking about a few tens of centimeters in the indoor environment if we want to keep a very broadband communication performance. And that's why one possible use case of terahertz is in the IIoT applications, so in the industrial domain that I was describing before, in particular to support intra-machine communications, so to replace cables with terahertz-based circuitry. In this case, we do not have to worry about the distances because we can stay in the short range. But if we want to operate at terahertz in the outdoor environment instead, we need necessarily to think about new ways of designing the communication protocols so that terahertz bands can be practically used. And so we have already increased the frequency from millimeter waves when we talk about terahertz, but now can we go even higher in frequency? Well, yes, if we go out of the radio frequency domain and we go into the optic domain. And this is by using visible light to communicate. And I'm talking about the frequency bands between 400 and 700 terahertz, more or less. And here we can use at the same time light sources, not only to illuminate the environment, but also to send data, to actually transmit information. And the first advantage is that we do not need to develop very complex and expensive radio frequency circuitry to make it feasible, this type of communication. We can simply use cheap LED devices. And this is one of the reasons why there is already a standard for VLC proposed by the IEEE, and that's why the research is much more mature than it is for terahertz. So it's a very promising solution to provide indoor connectivity. But we want to go in the outdoor domain instead, there are several challenges to be faced. One is the shot noise from other light sources, and in particular, I'm talking about daylight. So the sun will create interference for communication, and it's very difficult to manage interference from the sun. And also, VLC will not likely work well for the uplink. So VLC will necessarily have to be complemented with other RF technologies to cope with the uplink that, as I was saying at the beginning of this presentation, is gaining more and more attention for future networks. So it's okay to use it in the indoor, but for the outdoor scenarios instead, it's complicated. There is, though, one use case which is particularly relevant where VLC can make it a good solution, and this is for vehicle-to-vehicle communications. So we can use taillights and headlights in cars to communicate, to actually send critical information among cars. Even though, again, the effect of the daylight on the on these VLC-based communications is still to be figured out, and further research is needed in this domain. But still, it's a technology that is gaining momentum within the 6G future activities, and that's why I'm discussing about it in this presentation. So this is what I have to say regarding communication technologies. But besides the new spectrum, 6G will also transform the wireless networks by using new technologies that are not or part of the 5G discussion. And one is the so-called out-of-band estimation. So when we operate at high frequencies, I'm talking about millimeter waves, but also terahertz or VLC, as I have introduced before. We have the issue of how to estimate the channel. So the channel is at these frequencies is very time varying. So what we estimate in one specific time slot will be completely different from what we actually experience when it's time for transmission. So how we can ease the process of estimating the channel. One approach is to leverage channel estimation in the legacy spectrum, where everything is better, and then convert it in what we would practically experience in the high frequency domain. And this is challenging because we need a good transformation function that can relate in a good way the spatial correlation matrix we estimate in one frequency domain to what we actually will experience in another completely different frequency spectrum. So this is something that still need to be investigated. It's partially doable if we exploit the fact that the high frequency channel is sparse. So it's pretty easy to identify some portions of the spectrum where the information of the channel, like the angle of arrival and angle of departure, can be identified. For example, in this figure here, you can see that it's pretty easy to see that there are 6 dominant paths in this channel. And by estimating these 6 paths, it's possible to convert them into the high frequency domain and to exploit this information for making a proper channel estimation. So this is one good technology. And another one is the use of of integrating sensing with localization. One requirement in 6G is to provide accuracy, a very high accuracy for localization. And I'm talking about something like 1 centimeter accuracy in the indoor scenarios. And this might seem very challenging, and actually is challenging. The application I have in mind is for providing public safety in the indoor. So suppose that there is a fire in the skyscraper. In the skyscraper, you cannot leverage the geolocalization from GPS coordinates because it's not available indoor. So how can you identify whether within the skyscraper there is a person that's needing assistance? And how can you locate where exactly, in which room the person is located? You have to identify it, to find it, and to communicate this information to first responders or that are going to assist the person. And in this case, what you can do is to exploit the radio frequency signal to enable at the same time localization and communication. So by using the high frequencies, you can create a map of the environment, and you are achieving sub-centimeter accuracy if you use high frequencies. At high frequency, the wavelength is very short, and the accuracy of localization will be proportional to the wavelength. So if you reduce the wavelength, you will also increase the accuracy of the estimate. So once you have this map of the environment in the RF domain, you can project information you acquired on the angle of arrival into estimate of the location. And this works for both indoor and outdoor, and is particularly doable if we design terahertz-based localization in together with communication. So this is something that will see the light when within the 6G future activities. So now, what about the network architectures? So how will the network architecture need to evolve when we go into 6G? Do we need to change the structure of the network, or do we just simply need to evolve what 5G is already supporting? So one aspect of the research I want to focus on is this centralized RAN structure. So the idea is pretty simple. Instead of having several base stations that want to support the users, we can split the network into one or more decentralized units or DUs, which will be under the control of one big centralized unit. So what are the advantages of this architecture? Well, the first one is that we can have centralization and data aggregation. These DUs can perform observations of the environment and share this information with the CU, which will then make centralized network decisions, thus satisfying the requirement of making the network autonomous. And then from this architecture here, you can see that there will be just one single backhaul and several fronthaulls. So we can reduce the cost of the deployment of the network. So it's going to be a scalable solution. And one other advantage I want to shed light on is energy saving. We can implement the DUs with just a subset of the network functionalities, while the CU will have a complete stack implemented. So the DUs will consume much less energy than the CU. And overall, the energy consumption of the network will be drastically reduced. So in terms of challenges, what still needs to be addressed is, first of all, what is the optimal degree of separation between CU and DU that will allow for that will maximize the performance. I'm saying how many DUs can a CU support? If we associate too many DUs within the same CU, we will experience an increase in the backhaul traffic that this CU will need to manage. And if the backhaul link is overwhelmed with traffic requests, then will also degrade the overall performance of the network. So this still needs further investigation in the future. Another revolutionary concept is this so-called cell-less architecture paradigm. So the question is, how do we enable multiple communication technologies in 6G wireless systems? So I want to take the smart city as an example. In the smart city scenario, you will have different and diverse communication technologies together at the same time. For example, you will have Bluetooth or RFID technologies for the wearable devices. Then you have the LoRa or narrowband IoT technologies for sensors. And then we have the typical wireless networks that can operate at millimeter waves or at terahertz or even at visible light communication. And then you have the fiber optic communication networks and the cables to manage the backhaul and to connect the core network. So how can all these base stations support all these technologies at the same time? It's going to be unfeasible. So the solution is, as I was saying, a cell-less architecture. So we can extend or even remove the boundary of the cell and make the user connect to the network as a whole rather than to a single cell. So in other words, we can simply forget about cells. It's just the network. So there would be no handover anymore because there is no cell boundary at all. And it works well also with the concept of virtualization that is also gaining momentum in 5G. So there is no need for a physical place to install the hardware anymore. We can just simply consider software. And it's going to be, of course, less expensive for both deployment and maintenance of the network. And there will be no interference too. So according to the specific use case, the user may use different network interfaces, exploiting different complementary characteristics of the different spectra. For example, the sub-6 gigahertz layer can be used for the control of the network, where everything is stable and you don't experience bad propagation characteristics as you typically do in the high frequency domain, while the terahertz bands can be used for managing the data plane, where you actually want to exploit the full potential of the multi-gigabit per second data rates. So this is another important topic of research. And then one other big issue I was already mentioning before is bridging the digital divide. So providing connectivity in rural areas. In 5G, we talk about high capacity, low latency, and so on, but everything is related to where the connectivity is already there. We talk about the urban environment, and this is where the telecommunication vendors and the network operators will benefit the most from 5G rollout. But what about all these areas in the world that do not have broadband connectivity yet? And we are talking about 1/3 of the population that currently has no high capacity internet access. It's a huge amount of people that deserves better connectivity. So how can we provide connectivity to those areas? Well, increasing the network density, so providing more base stations in these rural areas might be unfeasible due to the energy crunch that we'll have, and also due to the fact that sometimes network operators do not see those areas as a profitable place to install telecommunication systems. So what we want to have instead is the so-called Internet of Everyone. So we want to provide connectivity everywhere, every time to everyone. And one way to do so is by using non-terrestrial networks. So this is a 6G specific idea. Instead of having the typical bidimensional network where we have the base station that provides connectivity on the ground, instead the idea is to deploy non-terrestrial platforms to cooperate together on the ground. And I'm talking about drones or even high altitude platforms or satellites at different orbits in the LEO orbits or in the GEO orbit. Um, there are several advantages of this paradigm. For example, we can use and provide connectivity even where in the rural areas where there is no terrestrial base stations, or even in the urban areas when the terrestrial base stations are unavailable. Like if there is a power outage, or if there is a natural disaster or a terrorist attack that jeopardizes these events can jeopardize the communication. And this non-terrestrial platform instead can provide a continuous coverage on the ground with very large coverage umbrella too. So improving also data broadcasting and relaying. And the energy consumption of the overall network will also be reduced because we don't need to power these devices every time and continuously as we have in the typical terrestrial base station, but instead we can just deploy those elements on demand when needed, like to support first first responders if there is an emergency. We deploy the UAVs and we support their connectivity only in this specific time frame in which connectivity is needed. So you can see that there is a great potential here too for further research. And then there are some other ideas from an architectural point of view, like the use of integrated access and backhaul. So the possibility to use and to have the backhaul traffic to be controlled wirelessly rather than using fiber cables. But due to time constraints, I will not go through the details of this aspect. Instead, what I want to talk about in the time I have is about how we can integrate intelligence in the network. Intelligence or artificial intelligence, machine learning algorithms, as you want to call it, is something that has already been discussed for 5G. But for 6G deployment, we have a completely different architecture. We'll have much more nodes and access points and users to control. We have more heterogeneous networks to support. We have integration of different technologies and applications together. And most importantly, we have stricter requirements for the services to support compared to 5G. So if AI so far is supporting control and prediction of the network, in the future, the intelligence will play a different role. We are talking about enabling URLLC in the extreme environment. We are talking about integrating different types of devices together, like the drones, the smartphones, the vehicles, and the sensors in the city. And the final goal is to support a fully autonomous network where there will be no need for human intervention anymore. The network will be completely autonomous, and this autonomy will be supported from an end-to-end perspective, from where the communication starts until where the communication ends. And in order to do so, machine learning will be important. So far, the typical machine learning algorithms that are considered are supervised or unsupervised learning, which cannot be doable when we increase the number of parameters to optimize, when we increase the data sets that are exchanged. And so reinforcement learning has been discussed for the latest 5G advancements, even though what 6G will likely support is a new type of learning, which is referred to as distributed learning. So we need the workload to be distributed across multiple machines, thus turning the centralized into a distributed system. And among all possible distributed learning solutions, one that is gaining momentum is federated learning. The idea is that each device trains a model of the environment through local data, and what the devices share is not the data, but is the update of their models. So we will save precious network resources because we don't need to share the data anymore. We can just simply share model updates. It's much more easier from a computation point of view. And we also, in this way, will address critical issues of the networks, like the privacy of the data, because data is not shared anymore, as well as who has the right to access those data. Of course, federated learning is a relatively new branch of research, and there are several challenges to be faced, like where will these data need to be processed? Do we need to process the data on board? If yes, then how can we do that in real devices, which are like battery constrained, like for UAVs? And if instead we delegate the burden of the processing of the data to some external clouds, then there is the latency for uploading this data to the edge of the network. And this also goes against the requirements of very low latency of 6G. So how to cope with this trade-off is still unknown and should be regarded as a very important research activity for 6G. The last topic I want to discuss with you about is related to autonomous cars. This is a seminar for the VTS. So I think that how to deal with autonomous cars and how to make it possible for vehicles to communicate together is something very relevant. The issue here is that we have several cars with several sensors, and all these cars will need to disseminate the results of their observations through their local sensors. And even if we increase the capacity of the channel by going into millimeter waves, for example, this might not be enough for allowing all vehicles to share all their sensors acquisitions. So the idea is to leverage the concept of value of information. So instead of sending everything, we should just send what's more important for the final receivers. And there are at least 4 questions to be answered. So where to transmit the data? So how frequently is the data dissemination, should the data dissemination be performed? When should we actually transmit? And what should we actually transmit? So which pieces of information will be more valuable for the receivers? And in order to answer these 4 questions, there are several aspects of the research that 6G will look into. And in particular, I want to focus on compression and detection of objects. So for as long as compression is concerned, while there are several compression algorithms for 2D images, like the results of cameras, what about LiDARs? LiDARs generate point clouds. It's a type of sensor that has been considered as a good way of improving autonomy in the car. But how to compress point clouds is much more challenging than compressing camera observations. So one possibility is to use 2D algorithms, so to convert the point cloud, the 3-dimensional point cloud, into a 2D image, and then apply 2D compression algorithms to the resulting output. And from some preliminary results, we are getting improvements. We see that these 2D algorithms will actually work better from a computational point of view than the algorithms that are specifically tailored for 3D point clouds. But another approach is to exploit semantic segmentation. So first, we can infer class labels to the LiDAR's point clouds, so we can identify what belongs to cars, what is a pedestrian, what is a building, what is the road, and then compress only the data that it's more critical to be shared. So we can avoid sending out pieces of data referred to the road, and we can just send point clouds for pedestrians or cars, which will be the most critical and valuable information for receivers to gather. And so how to integrate together the semantic segmentation and compression is something that is still to be discussed. We have performed some preliminary demonstrations which are proving that merging these two characteristics together is promising, but still something more has to be done in this domain. And also how to make it possible for object detection to be accurate and as accurate as possible. How many sensory data do we need? In this figure here on the left hand side of the slide, you can see this is the AP score, is the average precision, so the quality of the detection accuracy if we use only LiDAR acquisitions. And here is the same if we use at the same time camera and LiDAR information. And you can see that the final result is not very different, right? So it seems that LiDAR as a standalone technology can do as more or less the same as fusing together camera and LiDAR observations. The advantage of using LiDAR only is that we can reduce the amount of information that is disseminated over the channel, so improving also network communication. And so object detection is still something that should be done in the future, and should be we should do research more on this domain. So this is a summary of what I've just described so far. These are the four, let's say, the four main areas where the 6G technological advancements are looking at: the design of new architectures, the use of new new spectrum solution to improve the communication, and also how to make it possible for a more disaggregated and autonomous network to be deployed. And I want to conclude this presentation with let's say, a comment about this new fight, we can say, between telecom operators and vendors. So from one point of view, vendors, 6G is becoming challenges from several different points of view. And so vendors are spending a lot of efforts and money into developing new technologies that can be patented and sold. While at the same time, in the past, telecom operators have invested billions of dollars in 5G technologies, into buying bands, licensed bands for 5G operators, and what to make and fully exploit the potential of 5G before looking into a new generation. So we can say that maybe for the first time, the interests of telecom operators and vendors are diverging. They are not aligned towards the same path anymore. So we'll see how 6G will go, and we'll see how the research will go in the next few years. So with this, I can conclude my presentation, and I thank you all for your attention.
Thank you, Marco. It has been a wonderful presentation, and there was a lot of things, a lot of new things, and quite a bit learning for me as well. So while you were presenting, we got a few questions. So I would like to start with this one. So basically, thank you for your presentation. It's wonderful. What is the expected 6G deployment timeline? And since the 5G has not yet deployed, so what would you say on this?
Okay, so in order to answer this question, I can come back to this slide here regarding the standardization activities. I have to say that if we are going to have the same time horizon we had for the previous wireless generations like 4G and 5G, we can expect the standard for 6G to be completed around the end of this decade. So let's say within the 2029 or 2030, and then the next 5 to 10 years for commercial rollout and deployment. So we can expect the first 6G networks to be operative after the 20 after 2030, so around 2030 2031, as it is for 5G now. But for having a real 6G compliant network out there, we need to wait at least 10 to 15 years, I'd say.
Yeah, thank you. And before we go to the next question, I would like all the viewers that in a couple of weeks, we will have another very interesting seminar about writing the IPRs or patents. So we will have our guest who is one of the patent genius. So he will be with us and he will talk about how to write patents, what to patent, and how. I mean, all the details. I think you will enjoy it quite much. So you can just keep an eye on this channel, and then we will keep you posted about further details. So the next question we got is this one. Do you see quantum computing, network rendering, blockchain obsolete from an encryption cybersecurity standpoint, or is there room for both technologies?
Thanks for the question. I think that both blockchain and quantum computing are technologies that will have a very good activity within the 6G timeframe. It's important to check how they can be merged together, how we can make it both technology to be deployed at the same time. And this is something that is still quite difficult to have. There are several research activities that are being developed with the two different research. So they are being kept separate, while instead it would be good to integrate the use of these two technologies together. But I definitely see both of them as promising and good research opportunities in the future.
And then I have one question. When we were speaking of the visible light communication earlier in your presentation, so do we have any products, or I mean, if you came across any of those already in the market that we could use, or it is not there yet?
Well, let's say the device is already available because you just need to use LED. What you are missing still is how you can exploit the light for communication. So there are some test beds and some proof of concepts that have been developed for making VLC fully used, both in the indoor domain for sending light to your desk while you're working, and you can be illuminated and at the same time have communication. And also in the V2V domain, there are some test beds which use the taillights to send data. But I don't think there are off-the-shelf solutions to be purchased at the time being, or at least not something that is affordable to the most, I'd say.
Yeah, that is what I was thinking as well. So, but I think it was quite an insightful presentation from you, and I hope our viewers, they also liked it and they also enjoyed it as much as I did. And with
Thank you.
that, I think we are almost at the time. So we have few seconds left. So with that, I would like to thank you. Thank you for your time. And if we receive more questions, I will forward it to you.
All right. Thank you,
Yeah.
Taimur, for your for hosting this event, and also to the audience for attending.
Yeah. Yeah. Thank you for watching. And until next time, have a good day.
Thank you. Have a good day. Bye bye.
Bye.